Yes, so here I'm assuming there is some data like this. Here I've drawn like 3, 6, 8 points, and I don't really want to create an 8th order polynomial which passes through all those points. But you can see roughly, it seems like what can explain that data trend is probably a lower order polynomial which goes something like this, right? So maybe it's a 3rd order polynomial or 2nd order polynomial. So this would be the best fit or the inexact fit. And the goal here is to explain the trend. Okay, so your job is, in addition to figuring out which fit is good, you also need to figure out which polynomial to use. So how do you do that? Well, you typically would start off with, you look at the data and say, wait, line is not a good fit for that data, right? Maybe it's a quadratic term. So you'll do a quadratic fit. You'll do a 3rd order fit, maybe a 4th order fit. And then maybe a 3rd order fit has properties that it captures the trend. So you will say, okay, I don't want to go to 4th order. Let's stop at 3rd order. And maybe 2nd order is too simplistic for this, and so you'll stop. So there are some judgment calls you need to make. There is no exact science on what is the best line. So what I'm going to do here is giving you a few tools to do this best fit. The first one being linear regression. You might have seen this before. If you suspect that the best way to explain the data is through a straight line, then you'll use a linear regression. It's basically a 1st order polynomial. So an example of a linear regression line is f of x equals a plus bx, where a and b are constants that you need to figure out in order to best fit the data. Okay. So the way we do this is, well, we'll call this y. And what you'd have to your disposal is an ordered data set like this: xi, yi, x1, y1, x2, y2, so on till xn, yn. Okay, so this is your data set. And of course, you have some reason to believe that that data set is close to a straight, can be closely approximated with a straight line, something like this. Okay, so clearly, first step is to actually plot the data and then make a guess as to if a straight line is a good fit, and then you go with this equation. So let's say that we've done this step where we have the data, we looked at the data, we think that we suspect that a straight line is a good fit. So we start assuming y equals a plus bx. Now the question is, how do you compute a and b? Okay, it has to sort of explain the trend, but it doesn't really have to pass through all the points like we've seen before. So this is where we'll use calculus. We'll define an error term, E. E is error. And we'll define it in such a way that it captures the difference between the predicted value, which is yi is the predicted value, minus a plus bxi. So this is the true value, which we got from the data set. And this is the prediction in y, right? It comes from this formula. And we do this for all the data points, all the way from 1 all the way to n. And because we want to, we don't want to have just that sum, the subtraction, because you might have a case where you'll get 5 positive and 5 negative, and the sum of them is 0, that clearly is not ideal, right? So what we do is we square it, so that way we kind of penalize high value. So you don't want to have a fit where you have a bunch of hundreds and bunch of minus hundreds, so the sum is 0, but you got a very poor fit. The error is not 0. So square is a better way to quantify the error. So we want to minimize this quantity. So minimize E, and this gives us values or A and B from the minimization. So here we have to use calculus. So what we'll do is we'll use the, if you remember, if you have a quantity and you're trying to optimize it, minimize or maximize, what you do is you take the first derivative of that quantity with respect to the parameters, in this case A and B, equate that to 0. Okay, that's the first step. That tells you what the extremum value is, could be a maximum or a minimum. The second step is you take the second derivative of the same thing with respect to the parameters. If that quantity is greater than 0, it means it is minimized when you take the equal to, or if it is less than 0, it's maximized. So we're going to use that fact from calculus. We compute dA, but you know what? Before this, let me just copy paste that equation here, so that way we have easy reference to it. So I wrote down summation I equals 1 to n yi minus a plus bxi, and this only, you don't have to copy this again. I already wrote down the previous page. So from calculus, we can do dE dA equals. Okay, so I just have to differentiate this with respect to A. So the derivative of this whole sum of squares is A plus bxi, right? 2 times this quantity times, by chain rule, the derivative of this thing, which is going to be minus 1. Okay, and by calculus, what you do is you basically equate this quantity to 0. Okay, now let's see what we get from this this process. So I can factor out 2, and I can factor out a minus 1. So let's take that, factor those out, and expand this term. So we have minus 2 I equals 1 to n summation yi minus summation I equals 1 to n minus b summation I equals 1 to n xi. Yeah, I'm just distributing the summation across both. Okay, so I'm going to use a shorthand notation here. I'm going to write it as summation y. I don't want to keep writing the 1 to n. Okay, now if you sum this A, you just end up with n, right? If you sum A. Okay, so if you sum A, that is A plus A plus A plus A n times, then you get NA. That's what I wrote down. And then we have minus b times summation xi equals 0. Okay, so this gives me actually one equation. Let me just write it down in a form which I can then use later on. So NA plus b times, so summation xi times b equals minus summation yi. That's my equation 1. Now I need to do the same thing for b. So dE dB is so take the derivative of E with respect to B.
So I would have I equals 1 to n 2 times yi minus a plus bxi. And then I need to take the derivative of a plus bxi. So that would be minus xi, right? Because the derivative with respect to b equal to 0. Okay, so I'm going to factor out the 2 and the minus. So I'm left with minus 2. And I'm going to pull the summation inside the bracket. So I'll get, so note that this xi is going to be multiplied with this y. So I'll get xi yi minus a summation xi minus b summation xi square equals 0. And so I'm just going to rearrange this so that I get one equation similar to 1. So that would be summation xi times a plus summation xi square times b equals minus summation xi. That will be my equation 2. And what remains to be done is to use 1 and 2 to solve for a and b. That equation and this equation. Yes, I'll not go through the steps of how I go about solving for a and b in detail, but you should be able to do it because you have two equations, two unknowns, and it's fairly straightforward to compute a and b. So I'll write the formula, and you might have seen this before because linear regression is something which has been probably taught to you in a previous class. So solving for a and b. Yes, so solving for a and b from 1 and 2. So a is summation xi yi times x times xi minus summation xi square summation yi divided by summation xi the whole square minus n times summation xi square, and b is summation xi summation yi minus n times summation xi yi divided by summation xi square minus n times summation xi square. Okay, so the best way to do this is to sort of work it in the reverse. So we'll figure out what we need from the formula and then selectively generate that what we need from the formula, right? So we know that, so solution, we are trying to fit y equals a plus bx. And we know that a is summation see, so it's summation xi yi summation x minus summation xi square summation y divided by xi square minus n times summation xi square. Okay, and then b is summation xi summation yi minus n times summation xi yi. Okay, there are like some formulas, but they involve some summations, right? So what I suggest doing for such a problem is to actually generate these tables for all the summations, and it's easier that way. So what I mean by that is you would create a table like so, x minus 2 minus 1.6 minus 1.2 minus 1.0. No, sorry, 1.6, 1.2, 0.8. I'm going to run out of space over here. You will continue the next page. Okay, so what you notice is the following. You need summation xi, we need summation xi yi, we need summation xi square. We also need summation yi. So this is covered, this is done. Yeah, so we need these 4 things. Okay, so for those 4 things, what I'll do is I'll just generate a table for them, and then getting those things in the formula is simple as just summing the columns. So let's just do that, and let's do the exercise in the class. So I'm going to copy the table which I just put down there. We already have xi and yi in our data. This is there. We need to just compute these 2. So what you do is create 2 more columns. So one column would be xi square, another would be xi yi. Yes. So this is the first step to generate this table. The second step is to compute the quantities of interest. That would be summation x, summation y. So you just have to then easily, it's kind of easy now, you just have to sum the whole column, right? So I get summation x. The good thing is it's all symmetric, so it'll all cancel out to 0. Summation y, what I got was 7.255. Summation xi square, I got 17.6, and then 34.2939. Okay, so clearly I won't give you such a big table for the exam. It'll be shorter than this. It's too many lines here. 11 lines, probably 5 or less. Okay, so from this and from the formulas, I get A equals 0.6595 and B is 1.9485. Previous page, and I forgot to put n. N here is the number of points, the data points. So we have, I believe, 11. Yeah, 11 points. So n is 11. So what this is saying is that the model here is y equals a plus bx is basically y equals 0.6595 plus 1.9485x. Okay, so that's the answer. And then this will be, I'll probably ask you in the homework, but not in the exam, is to make a plot of what you have here. Plot the data and plot the best approximation for the data using your fit. And then you can see how good the fit looks. I have that already done. So got that. Let me just put it from my file. Okay, so the blue dots are the data. So the 11 points are shown there. And then the red line is the best fit line. So you can see that it sort of captures the trend. But in this particular case, none of the points pass through that red line. Okay, now this is valid, or this curve fit is only good if the data points, the blue dots, look like they line up as a straight line.